I'm Eric Roth with Nuance's BioCryo facility, and I have the honor of kicking off our new year of Tech Talks for first. So here we are. So I'm going to give a talk about spotting and solving EM misalignments. This is kind of a back to the basics approach to learning EM. Um, so, I find anytime I'm learning a new skill, I practice it. And once I finally feel like I'm really got a good grasp of it, I always try to be humble and get curious and, be open to being wrong. And I will try to go back to the basics and relearn things that I may have forgotten. Inevitably, there's some little step or something basic that I've just completely forgotten or didn't learn in the first place. And then that really helps me to, master the skill. Conversely, it's very easy to lose a skill. How many times have you sat down at a microscope, maybe after training, and thought, oh, well, these alignments look good enough. I can get some pretty good data. And you do that 3 or 4 times, and then you come back a 5th time, and then it's, really somebody threw it out of alignment, and then you're going, uh-oh, well, I guess I get bad data today. So, please, we don't want you struggling. Come ask us for help. We'll get you started, on relearning any skills that you've lost. Training is an ongoing process. We're not going to charge you more if you forgot how to, align an aperture or something. The model I'm using for this talk is our JUL 1400 TEM. And that said, most of these apply to most TEMs and even some SEMs. So the ways of doing things are slightly different, but the principles are all the same. All right, so one thing, just I hope this doesn't sound, too patronizing or mansplaining, but one thing I see a lot is when people are using the knobs, they're moving them just the tiniest bit at a time. And when you're doing that, often you're not going to see any change in your image. People are maybe afraid to make it worse, but really, if you're not seeing any change, then you're going to chase it. You'll go down to it, try to change something else, and then you'll be chasing a problem. So the more so don't do that. I find the better way to work the knobs is to really give them a good spin back and forth and make your image worse intentionally. Make it worse and then come back and see how it gets better. And then you just kind of dial it in, and eventually you'll get to the perfect spot. And it's a much faster way to approach things, especially when you're starting at a lower magnification or if you're really far off from alignment. And then you can kind of get closer and closer in with things. Sorry for the sound there. All right, so the next thing are the oculars, and this is another thing I see all the time. I'm sure people's eyes can't be this far off. Usually the oculars will be twisted one direction and then another direction, and then people try to look in them and they really can't see. So first time you sit down to any microscope, even a light microscope, I say take a look at these oculars here, and make sure that they are in their default position, because sometimes people will twist them in weird ways. So it's always a good idea just to line up, you see the plus and the minus here, and just make these lines in their default position. After that, now I'm doing this with one hand because I couldn't film and use 2 hands, but you should use 2 hands when you're doing this. But the oculars also move out side to side, and so everybody's ocular distance is a little bit different with how far apart your pupillary distance is, where you find focus. And so go in there and see what works for you. You'll have a much easier time when you're doing a lot of these alignments. So a lot of these we can do with the camera, but sometimes you really need to use the oculars and the phosphor screen, and sometimes that's a much better way to approach it. Also, another thing I see, don't forget to put down the focusing plate. If you look in the oculars, see a bunch of green, but you don't see your sample, you may have forgotten to put that in place. Another thing on the focusing plate, if you're not focused on the focusing plate, and what you can see here, we have, this is D for focusing with the oculars. And make sure you adjust that. So there is a little dot printed on the focusing plate. And if that's not in focus, you see, these are my little nanoparticles. You won't see those, and then you won't be able to use it. So once that is in focus, then you should be able to make your adjustments much easier. All right, so there are 4 basic controls to using an electron microscope. Now, we have lots of other parameters at play with adjusting the lenses and so forth. But when it comes down to it, we have just magnification, brightness, focus, and beam shift. So I'm just going to briefly talk about those before I get into the meat of my talk about identifying misalignments and figuring out how to make your image better. right, so beam shift is very basic. All beam shift does is move the beam X and Y on the phosphor screen. Not a big deal there. Focus, however, is very important. Obviously, focus is we're getting a focused image. But what's actually happening inside the microscope is that we have our lenses, and our electron beam is cascading from the electron source through apertures and lenses, and we have these two intersecting cones of electrons. And where those cones converge, if they meet at the plane of our sample, then we get a focused image. Now, when we're moving the focus knob left and right, what we're doing in the microscope, we're physically moving those cones up and down because our samples aren't perfectly flat. And as we move around, they get a little bit out of focus. And so we have three possible focal conditions that we can experience. So when the cones are converged directly on our sample, we get a truly focused image, and that's going to be the best resolution possible. And we all use digital cameras now, and so it's kind of hard to tell. Maybe your image doesn't look that good, but when you zoom in on it digitally, you'll see that you have much better resolution on features. The disadvantage to having a truly focused image is that it does have the lowest inherent contrast of the three focal conditions. Additionally, we're doing a lot more damage to our sample. As you can imagine, that beam converging right on that small point, we're irradiating the sample much more intensely. Now we also have over-focused condition, which if we have the beam up too high. You don't really want to collect images using the over-focused mode, but it can make it easier to find your samples, especially if you're doing something like cryogenic TEM. But the information you get from it is inaccurate. You get false information. Particles appear either like holes or hollow. You get sort of a double membrane effect to things. You can sort of see here. Alternatively, we have under-focus condition. So the under-focus condition is kind of a little bit more acceptable way to take images. You can see, so these black dots here are my 25 nanometer gold particles. And in my in-focused image, you really have a hard time making out anything else. But here we can actually see these little 5 nanometer gold particles are popping out there. Now, this is not in focus, and this is not the highest resolution. And this image here is a bit extreme in under focus condition. But you get these little glowing outlines to your features. It does improve contrast a little bit. So if you're publishing an image, probably want to publish in focus. But if you're giving a talk, sometimes it's nice to be able to just point out your features a little bit. So maybe a in-focused image and a slightly under-focused image can help you to illustrate what you're talking about a little better. All right, so the brightness knob. The brightness knob just contracts and expands the beam. So it's important to note that here we are. We can make our beam as small as possible. And so we call this convergence point is crossover. We're always bringing the beam to crossover by turning the brightness knob anti-clockwise to make it as small as it can go. Now, it's possible to continue in the anti-clockwise direction, and then the beam will spread again. But we call that reverse crossover. Now, we can use that effect to tell if the microscope is misaligned and to help us, to assist us with alignments. We never want to be imaging in that mode. So when you're imaging, remember, we always want to be rotating clockwise from crossover with the brightness knob. Now, brightness and magnification play with each other. So, well, they have a relationship. When we're moving magnification is we're essentially zooming in and out of the beam, but the beam does not change. So in this first video here, you'll see I'm lowering my magnification, and you'll see that the image doesn't really change except it gets smaller there, right? And so what we have to do if we're lowering our magnification is to spread the beam out, right? So that we have a nice even illumination to our features. Now, if we're going up in magnification, again, we're just zooming in and out of the beam. You can see the signal goes way down, and you can hardly see anything. So we're going to have to go anti-clockwise with the brightness knob to bring that beam back to the point where we can actually see our samples. Now, this relationship is important to understand mainly because of the camera. You can imagine here, if this beam, see how much more intense that is hitting the camera, we do risk damaging it. So, I have a rule on the 1400, but this should apply to pretty much all the microscopes, right? If you're going down in magnification, it's very, very important. Make sure you lower the phosphor plate first. and readjust your beam so that you're not hitting the detector too intensely. We can damage that. Now, if you're going up in magnification, obviously dose goes down, and that's not as big of a deal. But you're still going to want to lower the phosphor plate anyways, so that you can readjust your beam and get a more even illumination, a little bit more intense beam, and a better signal on your image. So anytime we're changing magnifications, make sure you lower that plate, and understand the relationship between brightness and magnification. Oop. All right, so now I get to the meat of the talk, as I mentioned before, spotting and solving misalignments. So I'm going to talk about 5 of these. And I'm just going to go through them step by step and give you another opportunity to learn. Again, it's okay to forget. There's a lot of information learning an electron microscope, and especially when you're doing other classes and so forth, it can get confusing and it's hard to remember if you're not practicing. Maybe you haven't been on the microscope in a couple of weeks. Or by the way, if you haven't been on the microscope in 6 months or whatever, feel free to let us know. We'll give you a refresh. It's not a big deal. All right, so aligning the condenser aperture. So this is the first thing you want to do, is we call it a full column alignment. We're going from top down. This can be very easy to do, and if you can do this, this is a universal alignment. You can do this on any microscope. Now, the features might be slightly different where the knobs are and which buttons you push. But we're only using 2 features here. We're using the beam shift, again, to move the beam, and the aperture knobs themselves, aside from brightness, of course. So what you want to do here first is want to know, well, what is the aperture aligned or not? So we can be able to identify that. So if you look here at this movie here, what I'm doing is spreading the beam clockwise, going anti-clockwise past crossover, and then continuing again back and forth. And what we're just doing is paying attention to how the beam spreads from center. We want to see an even spread, whether we're going clockwise from crossover or anti-clockwise to reverse crossover. Here in this movie, we can see where it's misaligned, and we're spreading the spot clockwise, and you get this translation, either an X or Y, or maybe a little bit of both in this case. So this is a misaligned condenser aperture. All right, so aligning the condenser aperture is very easy. And I realize this slide makes it look not so easy, but I'll talk you through it, and I'll show you a couple more videos that will hopefully make it so that you're not so challenged by it. First off, we're going to condense the beam to crossover, right? So we're going to go anti-clockwise, make that beam as small as possible. We'll use beam shift just to move that spot to the center. So remember, when the beam is small, that's when we're using beam shift. From here, we're going to spread the beam. Again, remember, always clockwise. We'll spread that out till it touches about the edge of the phosphor plate. Once we have it as large as we can make it and we still see it, we're going to use the condenser aperture X and Y to center that spot. From there, we can continue to spread the beam, again, clockwise, out to the edge. And then here we can just fine tune it with our little adjustments. And then we can check our work, right? So we should come back and see that the beam is now spreading evenly from center. So here's what it looks like if you're doing it on the microscope itself. So here's the phosphor plate and the beam. So again, we're going to bring that beam back to crossover. We're going to use the beam shift to center that spot. Again, when it's small, beam shift. When it's large, aperture knobs. So I'm going to spread the beam again clockwise with the brightness knob. And then here we will center that spot using, here's a little magic. And there we have it. So that is centering the condenser aperture. That's all there is to it, just those two features. Now, don't do them in the wrong order, otherwise you'll be chasing the problem. There we go. Now you can see that looks good. All right, so the next alignment we're going to cover is condenser lens stigmation. So we've got 2 lenses in the microscope. Well, maybe more, but the basics are the condenser lens and the objective lens. So the condenser lens can have an astigmatism to it. And so what we're doing here, rather than paying attention to how the beam spreads evenly, we're paying attention to the shape of the beam itself. We want to see that it's nice and round. So here, that's nice round going between crossover and reverse crossover again. And here in this video, we can see we get this kind of squish motion, this 90-degree translation where we get an oblique shaped beam. That is a condenser lens astigmatism. This one I find if I maybe load a new sample or even just after maybe an hour of imaging, it's always a good idea to come back and check up on this one. It does tend to drift a little bit in most microscopes. Now, there are two ways to align condenser stigmation. In field emission sources, we usually have a very collimated and very intense beam, and we don't have any unilluminated areas. So we have to align condenser stigmation based off of the shape of the beam. So what we can do with, as I showed you in the previous video, as you're moving between crossover and reverse crossover, you can see this 90-degree obliqueness to the beam. And what I like to do is just take the beam a little bit, again, clockwise from crossover, just a tiny bit, and so I can see that oval shape. And then I will use condenser stigmation, X and Y, just to make that feature nice and round. Then I'll go back and forth again and keep adjusting that until I don't see any change in the shape of the beam between forward and reverse crossover. So of note here, a perfect circle is not always going to be the perfect alignment. Sometimes a little bit oblique is actually correct. Rather than a perfect circle, what we want to see is just no change between forward and reverse crossover. So now if you're using one of the microscopes with, say, a tungsten emission or lab 6 emission, you may have some unilluminated areas of the beam. And if that's the case, you have a much easier job at hand. So all you need to do here is just bring the beam to crossover with the brightness knob. And then with the condenser stigmation, X and Y, just make your features as sharp as possible. And what you'll find is after you check that you'll see that between forward and reverse crossover, you have a nice even spread, no shape change. All right, so eucentric focus. Eucentric focus is really important. It's possible to get a really nice image without being eucentrically focused. But if you do that, the information on your screen may be inaccurate relative to the scale bar. So what happens when we move the focus knob, again, as I mentioned, the crossover of those cones where they converge, it physically moves up and down. And we want to be in focus, though, as close to the zero defocus plane as possible. And zero is just where the vendor, either JOL, Hitachi, whatever, they say this is where the middle is, where we think if your sample is perfectly flat, where the beam should converge on it. And again, our grids get bent really easily, and sometimes things are way off. So what we want to do is, rather than moving focus initially, once we load a sample, to get our sample into focus, we're actually going to be moving the sample into the crossover of the beam. So here's how we approach that. So first, you want to find some area of interest, whether your sample, piece of dust, really anything will work. And this is much easier. Well, it's more accurate to do it at a higher magnification, right? So sometimes you can start at a lower magnification and work your way up so that you can get really eucentrically focused. And it's important to make sure you reset the defocus value back to 0. So there's different buttons on different microscopes. My one here, on the 1400 says standard focus. On our 2300, it says lens reset. So we want to just set that back to 0. And then again, we're going to move the sample up or down into in the column. Now there's another feature on the microscope called image wobbler. And what the image wobbler does is it pivots those two intersecting cones at the 0 defocus plane. But you can imagine if my sample is below that, where those pivot points are, we're going to get a swing in our projection left and right by the time it hits the camera, as opposed to if it's pivoting on the point, we're not going to see any movement. So I'll show you here. This is what a typical eucentric focus alignment looks like. So when we activate the image wobbler, we see this movement, right? And so then I'm simply just moving the stage up or down so that the grid intersects at the 0 defocus plane and we don't see any movement. Now that's if your sample is relatively flat. And I've also seen people struggle with this, where you activate the image wobbler and you see something like this, and like, okay, well, what do I do with that? That's insane. I can't use that. So here's a tip for you. What you can do first, rather than struggling to figure out where the Z is when you have such dramatic movement, is first to just adjust Z without the image wobbler on, and just get it so that you're relatively in focus there. You can see so a little bit of XY movement, and then activate the image wobbler, and you'll find you'll have a much easier time finding eucentric focus. And here we are. So that's eucentrically focused. Again, we're in focus at the 0 defocus plane. All right, so now let's talk about voltage centering. Again, we want to be able to identify when we need to do this alignment. So in this first movie here, we can see a lot of movement in the features on my image. So if you look, the scale bar will not move, but my features will. Now, I'm not moving the stage here at all. All I'm doing is moving focus. So I'm going between over focus and under focus. And we see this dramatic movement in our features. They really should just stay in one place and then come in and out of focus. If you see that on your screen, that means that we need to do voltage centering. So what really is this? We have this nice round beam, and you would think that all the action should be happening from the center out. But it's possible, if we have a misalignment, that it's happening from far off on that beam. So what we can do here is activate, we have the HT centering here. So we have this voltage wobble. And what we want to do is just kind of determine which way we have this wobble going. So if I activate here, you can see sort of it's up and to the left. So what I did was I started with Y, because Y will fix all up and down movement. So now I only have X movement left over. So I'm going back to X and adjusting that. You'll see it moves up and down a little bit still. We're just kind of dialing that in, getting closer and closer, going back and forth between X and Y until we just have it pulsing in and out and not translating X or Y. And then we have our voltage centering complete. That's a really important alignment to do. If you see a lot of movement while you're adjusting focus, go back to that one. Because even if you have focus and stigmation accurate, they won't be once you go back to taking your images if voltage centering is off. So definitely a one you want to pay attention to. That one can wander a little bit as well, as you go through the hours of your imaging sessions. All right, next up, this is the one that gives everybody, I think, the greatest challenges. This is the last topic I'll be hitting today, sorry, is objective lens stigmation. So I'm just going to go through step by step, probably the easiest way to do this. Now, you can tackle this just using the oculars and just kind of paying attention to how the image looks. But that's after you've gotten really good at recognizing what an astigmatism in the objective lens looks like. But if you're not real familiar with what your features should look like, we can use the FFT, the Fourier transform, on digital micrograph. Now, this is the same opening it, whether it's the older versions of digital micrograph or the newer versions. We simply go to Process, Live, and FFT. So don't confuse it with this FFT because that's just a still image FFT. All right, so the FFT, as you can see, is very, very low contrast. This is actually decent compared to what I see often. So I'll show you a few tricks so that you can maybe help make this easier for yourself, just to even recognize the FFT. So first off, we wanted to have a clean carbon background if possible. If you're just looking at vacuum, you're not really going to see anything. This is much easier to do if your beam is more intense. But again, just be careful not to overload the detector. So keep your parameters in check. But a more intense beam makes that contrast a little bit more intense. Higher magnification is better. So on the our 1400 here, I recommend doing this, say above 30,000x at the very least. It's much easier to do it, say 80,000x. And on the field emission sources, you're going to be, in the hundreds of thousands of x. And also the use of the objective aperture. Now, you don't have to use the objective aperture, but it can assist in the contrast of seeing the FFT. Additionally, what I like to do is just kind of shrink that window down a little bit. That helps. It's almost like kind of binning the image. And it does make the features pop out a little bit just digitally. And lastly, what I'll do is I'll go up here to display. So there's two displays. You'll see one in the blue here and the one in the gray. Make sure you go to the one in the gray. That changes our features here and brings up our histogram. And then we can just slide gamma over a little bit. And I find that if I'm between, say, 30 and 35, I get the most pop out of that. And so we see a pretty big difference between here and there. This makes it a lot easier to recognize, see your features. So our goal is to get that feature in the center nice and round and as large and as round as possible. We have low resolution information towards the center and high resolution information as we go out. And so as we make the FFT larger, we start to recognize our errors more. Now, how do we do that? So what we're doing here is similar to aligning condenser stigmation with the brightness knob. We're using the focus knob to change the condition of the FFT. So you'll see that kind of 90-degree swing and squish again with the FFT as opposed to the beam. And again, we want to make that as round as possible. You see it's a little bit rounder here when it's small, and it gets worse as we get closer to focus. So what I'm doing here is I'm going between focus and under focus. And when it gets closer to focus, it's larger. So what this actually looks like is I'm going here, right? And so what I like to do is just leave it just slightly where I have a little bit of an under focus fringe. And so now I'm making it a little bit rounder. What you can see here is it's almost round, but as I adjust focus and get closer and closer to focus, we can see our errors are much more apparent. So now I'm spreading that beam, or getting closer to focus. You can see that's a little bit more oblique. And again, I'm adjusting that with X and Y to make that nice and round. So how do the X and Y knobs work? Y, so they're not quite intuitive the way you would hope they would be. But Y adjusts the pitch, sort of. We have this kind of on a 45 degree. And so if you get that either in a straight up and down kind of oval or in the Y direction, or so the X direction, you can then adjust X. The X knob moves it in X and Y. And so that's how you can kind of fine tune. So usually I have an FFT and I see that it's an oval and it's off to one side. So I usually first approach Y and I try to make that as up and down or as even as possible before adjusting X. That's what makes it easier for me. Another features that you can use here are the regions of interest. So if you right click on the screen, you'll see we've got this little region of interest, ROI. You can draw a rectangle, so that way you can see what your pitch is looking like when you're using the Y. You can also use the region of interest to draw it, well, it says the oval, but what you do here is hold down Shift, you put your mouse right in the direct center, and you pull out, you can make a circle, and then that makes it easier to tell if you actually have a circular form in the FFT and the Fourier transform. From there, you should have a very nice clean image with objective stigmation. So that's my talk for today. I hope it helped. I hope you've learned something today. And at the very least, you're maybe not afraid to ask questions and try to relearn things that you may have forgotten or you've gotten out of the habit of learning. So again, I just want to wish everybody a happy new year. Thank you for attending my talk.